I'm picking up where I left off in the comparison between the Siglent and the Rigol, that is the Siglent SDS1000, this scope here, and the Rigol DS1000Z. And if you watched part 6 of that set of videos, you'll know that I was in the middle of doing bus decoding when I decided to end that series and move on to a different kind of comparison. And so that's what I'm picking up with here now. You may see what is going on the screen here is pretty much where I left off. That is, I'm decoding an RS-232 bus with the Siglent, and you may notice that I have the list feature turned on, and I'll zoom in here so that you can see it a little better. There we are. And you may recall that the what we were decoding is shown here, and also down at the bottom is the word Rigol followed by a space followed by the DS6000, which is the name of the board that generates the signal that we're using. And so let me show you there is the signal itself on channel 1 of the Siglent, and then down below that is the decode. 52 is of course an R, and then I, G, and so on. And you may also recall, if you watched part 6, that the reason I stopped and decided to change gears is because I discovered, much to my discomfort, that the Siglent does not do an ASCII decode. And so what I wanted to do is to switch to comparing the Siglent with the Rigol and with the Analog Discovery. The Analog Discovery is a device that plugs into a PC and provides a variety of things, including a 2-channel oscilloscope, a 2-channel arbitrary waveform generator, a 16-channel logic analyzer, and so on. And I'm not going to get into the Analog Discovery too much. The Digilent website has many excellent videos on that. What I am going to do is compare with the what the Analog Discovery does with the same signal. And you may notice here what we have is a decoded signal. It's exactly the same signal that is being decoded by the Siglent at exactly the same time, but you may notice here that there is a R, I, G, and then continuing over to the right is OL. The important point to make here is that, in my opinion, the Analog Discovery does a far better job of decoding a serial bus than the Siglent, in large part because it does a full ASCII decode. That is, it not only gives you the hex values, but it also gives you a display of the signal itself and decodes that hex value into the ASCII equivalent. So what I'm going to do for the rest of this part is I'm going to do a quick review of RS-232 and UART for those of you that may not be familiar with some of the history, because it sometimes gets confusing. RS-232 and UART are not the same thing. Many RS-232 implementations use UARTs, but UARTs can be used for other things, and RS-232 is not a UART. It is a bus standard, including voltage and signal levels and other specifications. So I'm going to talk a little bit about that, And if you're not interested in that part, you might want to skip to the next segment. If you remember when you used to connect peripherals to your PC with connectors like this is a DB25, then you probably don't need what I'm about to explain. What I'm going to explain is a little bit of the history, and the reason I get into this is there's a lot of confusion, particularly among people who use embedded controllers, various ARMs and things like that, about the difference between a UART and RS-232. And some people use the terms interchangeably. That's not technically correct, but here is a little bit of the history. The original UART was actually designed by an engineer at Digital Equipment Corporation for one of the early PDP computers. And it took up a whole circuit board. In other words, it took up as much space as just about this entire PC motherboard, which, by the way, is ancient and therefore completely obsolete. And at about the same time, or a little bit before that, the Electronic Industries Association, or actually what used to be called RETMA, the Radio Electronic Television Manufacturing Association, picked up on trying to develop an interface standard for actually for teletype machines, which at the time used a 60 milliamp current loop. What they defined was a radio standard number 232. Now it shows you how long ago that was, because they were still using RS as a radio standard. And the first radio standard for 232 used a connector like this, a 25-pin DB25. It worked on plus or minus 15 volts. In some implementations it was plus or minus 12 volts, but the standard actually said 15. Some people actually stretched that and used 25 volts. But the basic standard was a bipolar, that is, it would swing between positive and negative to generate the marks and spaces of the old teletype. And it converted from a current loop interface to a voltage interface. Now, over the years, the UART invented a DEC, and the RS-232 standard, developed by the Electronic Industries Association, eventually merged into one common idea, which is a programmable device that could be put on the bus of a personal computer or a mini computer, and you could then program the serial characteristics of the device. Now, in the early days, there were many signals that operated on RS-232 because they were originally invented to handle modems. And it included things like data set ready, data terminal ready, receive and transmit data, and so on. This is what some people call a breakout box or a tester for an RS-232 of the day. And you basically used it to troubleshoot when you weren't getting the right signals. Eventually, the DB25 got reduced down to the smaller form factor, and of course a number of signals were eliminated, including things like data set ready and so on. It also began to be used for a lot of other purposes besides modems. So, for example, at one time you could plug a mouse into a RS-232 port, and it would run off of the UART. So, of course, what you may see over here is a collection of different adapters and gender changers and other things that were needed in the day. Eventually, the whole idea of using the RS-232 standard fell into disfavor, and people started just using a 5-volt UART. In other words, the basic UART, which by then had been reduced to a single integrated circuit. The first ones of which I think were the 8250s that were produced by National, and also later by Motorola and I think TI. At any rate, they became ICs, they got incorporated on boards. Today, those UARTs are actually incorporated inside the processor. So in addition to all the other things that are included in there, they also include a UART to provide serial interface. So I think that's enough history and background and why RS-232 is not the same as UART, but they do tend to get mixed up, and you see them often mixed in the literature. So now I think we'll get back to comparing the various decode options for buses. Now what I have set up is the Rigol DS1000Z. To decode the same RS-232, and at the top, of course, is the waveform itself, and then down below I have it set actually to decode both the receive and the transmit. There are 2 decoders in the Rigol. There also are 2 in the Siglent. But the difference here, I think, is significant. If you notice, what we have is an actual ASCII decode. That is, the specific ASCII characters are shown, R-I-G-O-L. Now, the Rigol has the ASCII, which the Siglent does not. The Rigol also has the ability to decode RS-232 in binary, hex, or decimal. Now the Siglent, as far as I can tell, only will do hex decoding, so it won't produce this. You can do all of this in a table and some other things that I'm not going to go into at this point, because as far as I'm concerned, the fact that the Rigol allows ASCII, full ASCII decode, and the Siglent does not, means that if you're going to use a scope in an RS-232 decode, then I would say go with the Rigol. I think Siglent needs to rethink their decode options and add an ASCII decode. So that sort of concludes the comparison between these two. I think what I'm going to do now is I'm going to set up a decode on an even better scope, a Rigol 4000, and show you how that decodes an RS-232 bus. And of course it's basically the same decode, it's just that the 4000 is a much better scope and also a much more expensive scope. Now we set up to do the RS-232 trigger and decode on the DS4000. Let me turn on a little more light here so you can see what we're dealing with. Now the DS4000 is a much better scope than either of the two that I've been comparing otherwise. But I thought I would show you that basically the decode on this one is essentially the same as the one on the much cheaper Rigol DS1000. Once again, the reason that it might be important is if you're doing RS-232 decode work, you don't really need a scope like this. This is actually it's a 300 megahertz or 350 megahertz scope. It actually goes out past 500 megahertz. The 3 dB point is about 516 megahertz compared to a megahertz. But because RS-232 is fairly limited in speed, you don't even really need a fast oscilloscope. The Analog Discovery that I showed you earlier is perfectly adequate. There is one thing that I thought I might show you because it's a little trick that helps a lot when you're trying to decode. You want to freeze the data, and the way you do that is you use this run stop button And you'll notice there the data is kind of flashing by. It's kind of hard to see what it is. And then you stop it. Now, what I have found is the best way to do this is to actually increase the sweep speed until the until the decoder can no longer fit the data into the little packet areas. Then stop the scope and expand it out one. The reason if you do that is now you can use the horizontal position control to scroll through looking at your decode. Now, there is an even better way than this to do the same thing using the record features of scopes like the DS4000. Unfortunately, the DS1000's record feature, while it can be used to do this, it's much harder to use. It doesn't have the scroll features that this scope has. It doesn't have the analyze features, and so on. So for basic RS-232 decoding, the DS1000Z is a good scope in my opinion. If you're doing really complicated stuff where you're looking for errors, random errors in a long RS-232 string, you pretty much have to go to a scope like this, primarily because it has the superior record capability. Not because it's a faster scope, but because the record and analyze features allow you to look at very long strings of RS-232 data and find places where you have exceptions and so on. So I think that about wraps up what I wanted to say about RS-232 decode, and I'm going to end this particular video at this point. I've now set up the Siglent SDS1000 to decode an I2C or an IIC bus. Once again, the data that's being sent is Rigol, and I'm not going to go through the setup on the Siglent because, as you'll see, I really don't consider the decode in the Siglent to be adequate if you're actually working with buses. In other words, it's somewhere between a toy and something you can use, but it does not decode into ASCII or any other format. But let me show you what the screen is showing, and you'll notice that up at the top we have the data, and the data that's being sent is Rigol. Now I'm going to stop the scope so that it will freeze and hold the data, and then we'll move in here and hopefully we can get it to there we are. Okay, and you may notice that on the top line I have it triggering on 52, which is the letter R in ASCII, 52 hex, and across the screen you can see R and then I, G, O, L. That's for F, by the way. It's hard to read, and that's for C. But that is the Rigol that the board is sending, and so it is properly decoding it into hex. However, if you were using this in any kind of a regular environment where you had to decode these buses on a regular basis, I really don't think you would find this to be a satisfactory situation. So once again, I'm going to suggest that just as with the RS-232 decode, the Siglent decode for I2C on this scope is, in my opinion, inadequate. And so I would not buy the decode package for the I2C, just as I wouldn't buy it for the RS-232. So now let's move on to the next, which I think is going to be the Rigol equivalent in the I2C mode. Here is the Rigol DS1000 decoding the I2C bus. Zoom in here first and let you see at the very top is the S clock signal, and the next line down in blue is the SDA signal, and then below that is the decode, and as you can see it's RIGOL, which is what the board is putting out. Now once again, as I explained, the Siglent will not do an ASCII decode as this one will. Both the Siglent or the Rigol will do a hex decode, but for reasons that I have stated previously, I really consider it necessary to have an ASCII decode if you're really going to be working with these buses. Now once again, I'm not going to show the setup on this scope. I'm actually going to compare this now with the Rigol 4000. Basically the purpose of that is to show that this DS1000, when it comes to SPI decode, just as with RS-232, in my opinion is every bit as good as the 4000, even though the 4000 costs 4 or 5 times as much. So let me set up to do that, and we'll come back with the Rigol 4000. I have the I2C signal connected to the DS4000. At the top is the S clock. At the bottom is the SDA, channel 1 and channel 2. Now what I'm going to do on this one is I'm actually going to walk you through the process of doing this. It is exactly the same on this scope as it is on the Rigol DS1000, and the setup is basically 3 steps. The first step is to get the scope into a mode where you can set up the trigger and decode, and all that involves is pressing the auto key. That will get the trigger levels set approximately right for, in this case, channel 1. And what I'm going to do is lower the time base now, that is longer time per division, until you can see what's going on here, and you'll notice there are some gaps, times when the clock is not sending. That's in between each data group. So you now have the scope triggered. I'm going to run it out a little bit. The second thing you want to do is to set up the actual I2C trigger. And to do that, you go to the trigger menu, which is over here. I told you wrong. I hit the trigger mode. The trigger menu is down here. And you may be able to read it. It says type edge. Let me now zoom in a little bit on the screen itself. So you select the type, and then you go down to the I2C, which is there, and you push the multifunction button. That selects I2C trigger. Now you can set up a series of options. SCL, or S clock, is set to channel 1. SDA is set to channel 2. It says start. I'll show you what the options are there. You can have all kinds of different start functions. I suggest that, at least when you're first learning this, that you use the start when start rather than when restart. Restart is the same as start, it's just that it's a start that occurs after a start. So there'll be a start, and then before it finishes, it'll restart. So we're going to do start. We'll now adjust, and you may notice that the trigger level is down here on the SDA, and that's proper. It'll do that automatically for you. That is, when you adjust the trigger button or the trigger level over here, this control, it will automatically adjust the SDA. You notice the little dotted orange line, the SDA trigger. Now I'm going to slow the sweep down just a little bit more. Then I'm going to go to decode. Now here is a place where this scope and the DS1000 is slightly different. In this scope, the decode is right here on the front panel. On the DS1000, it's in the math menu, but it's basically the same thing. You select decode, and it asks you what kind of decode do you want. You select that one, go down to I2C. It asks for the bus status. The S clock is channel 1, the SDA is channel 2. The S clock trigger is right there. The SDA trigger is right there, and you may notice that almost immediately up above you start getting data. I'm going to slow that down still further, and you'll notice that it's in hex format. I'm going to do a copy trigger, and then I want to change the format to ASCII. And you'll see, I'm going to go back out. Now I'm going to stop the scope at this point. That is, I'm going to press the run stop key once so that it will stop. You'll notice in the upper corner here it says stop, and you'll see the data that's being displayed. It's the D means data, so data R, data I, data G, O, L, and then a hex 49, and then the R again, and it continues to repeat. So this is the basic way that you set up to decode an I2C bus. In review, it's fairly simple. It's 3 steps. Step 1, press auto. Step 2, set up the trigger for an I2C trigger. Step 3, set up the decode for an I2C decode. And then adjust the various parameters the way you want it. But you will notice that one of the things that's kind of important is that you adjust the time, that is the time per division, so that you get whatever length of packet you want to display. Now, there may be times when you have a very long packet, and as I showed you in another video earlier, in that case what you want to do is you want to slow the scope down even further and then stop it. At that point, you have many decodes. Now, speed up until you see the part you want, and using the position control, the horizontal position control, move back and forth in this data, as you see there, looking for whatever it is that your particular search is focused on. So in other words, here it has sent Rigol, Rigol, and then there has been a gap. Then it sent Rigol, Rigol again. And so on. By using this technique of going to a very slow scan or very large time per division, stopping the scope, and then increasing or then lowering the time per division, or increasing the sweep speed to spread things back out so that you can actually read the decode, you'll find that finding various places in the sequence, particularly if it's a long sequence, will get a lot easier for you. Well, that kind of concludes this. I'm going to move on now. Now we're looking at the Analog Discovery, set up to do an I2C decode of the same signal. We'll start over here. You'll see that I have an I2C bus defined there with the serial data line on DIO0 and the serial clock line on DIO1. It's set to trigger when the SDA is low and the clock falls. In other words, falling edge and a low on SDA, which is the start condition. And you notice that the first that it shows is a read from hex 18, followed by hex 52, which is an R, then a hex 49, hex 47, I, G, O, L, and then a stop at the end. Now this is a 125 kilohertz clock, I2C bus. Most of them are in about this range, at least the ones that are on chips like the Arduino and the Raspberry Pi and things of that sort. There are some faster I2C buses, but given that the Analog Discovery will handle up to 10 megahertz, I don't anticipate any problems. And so my conclusion is that the Analog Discovery may be exactly the right solution for bus decodes. Now, you may notice one thing, though, that is a little disappointing. It does not do an ASCII decode of the data values. It just does it in hex, which, as you recall, was one of my criticisms of the Siglent. But one advantage of this Analog Discovery is it does have 16 input channels, so you can do wider buses, and you can also do things like SPI, which require 4 signals, or at least have 4 signals, and sometimes you need to be able to look at all 4 of them. That is the clock, the MOSI, which is the master out slave in, the MISO, master in slave out, and the chip select. So I'm not going to go any further on this. What I am going to do is kind of wrap up this series with a little bit of an overview, and then I hope you'll be able to see at least my reasons for suggesting certain features of each of these 2 oscilloscopes and the Analog Discovery in these bus decode cases. Here I've set up the Rigol. In this case it's the MSO, but the equivalent of the DS1000Z for an SPI decode. You can see over here we have the decode in the upper right hand corner. The decoder is on. The clock is set to channel 1. That's this yellow line at the top. The MISO, that is master in, slave out, is turned off. Master out, slave in is set to channel 2. And that's this second line in blue. And then the chip select is channel 3. It's not shown on this menu, but it's one further down. And so let's take a look at what we actually have here. So what we have is the clock and data. This is a start signal for an SPI bus, and it's the start signal that occurs when chip select is asserted. In this case, chip select is active low, so it's really chip select bar if you think of it that way. And then down below is the decode in hex. You'll notice that it's the numbers are 97, 97, 97, 97. The way this particular board works is it puts out 4 bytes of data all with the same number. Then it increments that number and puts out 4 more. It will then go into a mode of 2, and it'll put out 2 numbers and so on. I've stopped the scope. You'll see up here that the run stop is stopped, and that's so that I can display just one, because of course this is changing all the time, and so if you don't stop the scope, you're constantly overwriting what you're seeing, and you just see gibberish on the screen. So this is basically the way that the Rigol SPI decoder works. It seems to be pretty easy to use, but I'll point out something that's rather important. You may notice I'm using 3 channels. And to properly decode an SPI bus, you do need 3 channels. Now you also, if you're going to look at the response, in other words, the meso signal, you need 4 channels. So that's one reason that if you're going to do SPI decodes, you really need a 4-channel oscilloscope. And I really don't think that the decode on the Siglent would ever be satisfactory. The reason is, you'd be looking at what the master sent out. Then you'd have to reconfigure everything and move a probe around on a 2-channel scope I'm talking about in order to look at the response, that is the MISO, M-I-S-O, instead of the M-O-S-I. By the time you've done that, that signal is long since gone, and so then you have to kind of hope you catch the response, and you'll never be able to display on the scope at the same time the master's signal out and the master signal in, that is the slave's response to the master, on the same scope screen. And so the bottom line of all this is, in my opinion, if you don't have at least 4 channels available to you, it's really kind of pointless to think that you're going to be able to do any serious SPI decoding. So let me stop at this point and then show you the same thing on the Analog Discovery, which is in essence a 16-channel logic analyzer. We're now displaying the output on a personal computer of the Analog Discovery, decoding the same signal. Now, because I've stopped this at a different point, the decode is slightly different, and you may notice that in this case the decode is a try to zoom in a little bit, hex 87. Once again, 4 bytes, hex 87 4 times in a row. The signals you're looking at here, the top signal is the chip select, the second signal is the S clock, and the bottom signal is the MOSI, or master out slave in, same as we were looking at on the Rigol. Now at this point it has incremented, or rather decremented, the counter by 10 hex, which is in essence 1 bit shifted in hex. And that's the reason why you're seeing 87 here instead of the 97 that we saw on the other. But it's, if I had been able to stop both of them at exactly the same time, you'd have seen exactly the same data on both. So my conclusions actually are that for the purposes of a laboratory where all you're trying to do is to teach the use of buses, the Analog Discovery is probably a better approach. It's no more expensive than adding the decodes to the scope, and because you have a separate unit that can also do many other things, you can have stations, one of which is being used, for example, to do an SPI decode or an RS-232 decode or I2C decode, while somebody else is using the the bigger oscilloscope, the Rigol or whatever the oscilloscope is. And that's one of the reasons that I think the Analog Discovery is really the optimum. It's very inexpensive. It can be, so you can afford several of them, many stations. It's nowhere near as fast as a good oscilloscope. It's only 10 megahertz, but it really is, in my opinion, the best approach for a university lab environment when it comes to bus decodes. So I'm going to conclude bus decodes, triggering and bus decodes at this point, and we'll do a little bit of an overview and wrap up, and then maybe we can conclude this whole series.